We will now study a kind of networks that are called physics-informed neural networks. So these physics-informed neural networks are networks that are somehow trying to solve a physical system. So let's give a very simple example. So let's say that we are interested in solving the 1D heat equation. So the 1D, one-dimensional heat equation. So it should respond to this differential equation, which is partial in time and partial in time, partial in space. So let us let's move this term to the left hand side. So we will define a function f that somehow measures what is the difference between the partial over time minus the second derivative with respect to space. And we know that for this solution this is 0. We have also some initial conditions. So let's say that we have some initial distribution of heat here in the bar. So it is a very thin bar or very thin filament with some initial distribution of temperatures, and we have some boundary conditions. So for instance, we keep both ends of the filament at 0 degrees, and then we have some physical or some losses. So we want the network to predict U. So this U depends on the space and time, and it will, if we have some measurements of how these temperature evolve over time, we can put them. So this is our prediction, this is our measurements. Then we have the initial conditions, so there is a loss for respecting the initial condition. There is another loss respecting the boundary conditions. And this is the most important one. That is how the physics, we know how the physical system behaves. So this f should be 0 at all times. In practice, as the neural network is learning, this u at some point, especially at the beginning, will not be 0. So it will have some residual, and then we try to force it to be 0. And we sum this for discretization of space and discretization of time. Here we have the same. Okay, good. So let's see how we can do this code. So yeah, this is just imports, and then here is our neural network. So the neural network is just very simple network. So just some linear, some hyperbolic tangent. So very simple network. And we have our model. So okay, and our model will depend on space and time. Okay, then yeah, these are just setting the sampling in space, in time, the boundary conditions. So we are randomly distributing the sampling in space and time, and we are randomly we are putting the boundary condition, so on those time. So also the time of the boundary condition is random, and then we have the initial profile of the of the temperature. So let's say that our profile is this one. Okay, then how do we train this network? So the network will make a prediction for the current for the time and space that we are evaluating. So for this space and time, now we compute the derivatives of what is the u predicted. So this is just to compute this physical function that we have here. So we can compute what is the derivative with respect to time, derivative with respect to x, the second derivative, and then we can construct the function f. And what we want is that this physical residual, the physical residual is just the term here, so it is as small as possible. So we will put the loss on the average of the physical residual, and then we will put a loss associated to not respecting the boundary conditions and not respecting the initial conditions. The total loss will be the sum of the three. So we have said here that xf and tf requires gradient, okay, so that we can compute these derivatives, and then we compute the loss and optimize, give one step of optimization. So the weights of the neural network will be updated by this optimizer. And yeah, we can see here how the loss function evolves. So we can see that from the very beginning, the very first epochs, it already decreased quite a lot. May increase from that because yeah, in this learning rate thing, we may jump to a region that is not good, but then it stabilizes. Okay, and once we have learned the neural network weights, we can use it to predict U. So now you can put your x values, your time steps, and then you need to put them as tensors because the model only accepts tensors, and then you make what is the prediction of the U function. You can plot those. So here is a nice example of how we can solve a physical system using a neural network. So the neural network, what receives is the space and time, and then it has to respect the differential equation and the boundary conditions, the initial conditions, and so on. Here we have another example in which we have a hybrid neural network. So a part of it will be provided by a neural network, but other part of the system is defined by ordinary differential equations. So let's say that we start, we observe some displacement, so of a system like this, of a spring system like this. So it has some resistance, so it has some inertia, and we observe the displacements of that system, and we want to know what was the force that was applied to the system. So there is some force here. So what is the force? The force will be given by the neural network. But once the neural network is given the force, given that we know what are the initial conditions of the system, we can try to minimize the distance between the observed behavior and the predicted behavior by our simulation. So our simulation, part of it is physical, but the other part, that is the interesting one, that is what was the force. Okay, so then we have the network that will learn the force, and the force only depends on time. That is what we have here. The force only depends on time. Unfortunately, I have called it x, but yeah, it is time. Then we have the simulated mass spring damper. So these are the physical. This is the physical behavior of the system. So we have an initial position, initial velocity, and then we have the differential of time. So we go for all time points. We compute what is the acceleration, and then we update our velocity, we update our position, and we iterate this for the time points. So now we define our model, and then we predict what is the force according to this model. The beginning will be 0, and then we have our initial position, initial velocity. We simulate with this force and this initial velocity and position and the time. So we have what will be the position of the system at all points. We compute our losses. The loss is the distance between the simulated position and the measured position, and both as tensors, because the GPU only understands tensors. And then we simply backpropagate this loss so that we update our network weights. We can see again how the loss starts with very large error, and then the error is drastically decreased until we have this simulated behavior, and this is the estimated force. So neural networks do not need to be just black boxes. So they are useful to represent functions, and then these functions can be used in whatever way that has some physical meaning. So as long as you have a system on which you understand the physics, you can combine the neural networks with the capacity of the neural networks to learn functions, and the capacity of the differential equations to predict how a system under some forces or under some functions will behave. So this can be a very powerful combination.